Welcome to this tutorial on memory efficiency in NumPy. In this video, we'll explore how to optimize memory usage when working with NumPy operations. Understanding memory efficiency is crucial for handling large datasets and improving the performance of your data processing pipelines. Let's dive into the techniques that will help you write more memory-efficient NumPy code. NumPy arrays can be stored in memory using two different layouts. Row major order, also known as C order, stores elements row by row in contiguous memory blocks. This means all elements of the first row are stored together, followed by all elements of the second row, and so on. Column major order, known as Fortran order, stores elements column by column in contiguous memory blocks. Here, all elements of the first column are stored together, followed by the second column. Understanding these layouts is important because they affect how efficiently your operations run. You can easily check the memory layout of your NumPy arrays using the flags attribute. To check if an array is C-contiguous, meaning it uses row major order, you access the C_contiguous flag. To check if an array is Fortran contiguous, meaning it uses column major order, you access the F_contiguous flag. By default, NumPy creates arrays in C order, which is why C_contiguous returns true and F_contiguous returns false for most arrays. Choosing the right data type is one of the simplest ways to reduce memory usage. Different data types require different amounts of memory. For example, int64 uses 8 bytes per element, int32 uses 4 bytes, and int16 uses only 2 bytes. If your data fits within the range of a smaller data type, you can significantly reduce memory consumption by choosing that smaller type. This becomes especially important when working with large arrays containing millions of elements. Let's see a practical example of data type optimization. When you create an array without specifying a data type, NumPy defaults to int64, which uses 40 bytes for an array of 5 elements. However, if you explicitly specify int32 as the data type, the same array uses only 20 bytes. That's a 50% reduction in memory usage. You can check the memory consumption of any array using the nbytes attribute, which returns the total bytes used by the array. Understanding the difference between views and copies is essential for memory efficiency. A view is a reference to the original data without creating a new copy. This means no additional memory is allocated, making views extremely memory efficient. On the other hand, a copy creates a completely new independent array with duplicated data. This uses extra memory because you now have two separate arrays in memory. Whenever possible, use views instead of copies to conserve memory. Slicing operations in NumPy typically create views rather than copies. When you slice an array, you're creating a view that references the original data. This is why modifying a view also affects the original array. In this example, we create a view using slicing, then modify an element in the view. When we print the original array, we see that it has also been modified. This behavior confirms that slicing created a view, not a copy, saving memory in the process. In-place operations are another powerful technique for memory optimization. When you perform a regular operation, like multiplying an array by 2 using the asterisk operator, NumPy creates a new array to store the result, consuming additional memory. However, in-place operations modify the array directly without creating new arrays. You can use augmented assignment operators like asterisk equals for in-place multiplication. Many NumPy functions also support an out parameter, allowing you to specify where the result should be stored, which also avoids creating temporary arrays. When working with extremely large datasets that don't fit in RAM, memory-mapped files are your solution. Memory mapping allows you to work with data stored on disk as if it were in memory, without loading the entire file into RAM. You create a memory-mapped array using NumPy's memap function, specifying the file name, data type, mode, and shape. The data is then accessed on demand from disk, loading only the portions you actually need. This technique is invaluable for processing datasets that are larger than your available memory. Let's review the key strategies for memory efficiency in NumPy. First, choose appropriate data types to reduce your memory footprint. Using smaller data types when possible can dramatically decrease memory usage. Second, use views instead of copies whenever you can to avoid duplicating data. Third, leverage in-place operations to modify arrays directly and avoid creating temporary arrays. Finally, for very large datasets, use memory-mapped files to work with data on disk without loading everything into RAM. By applying these techniques, you'll write more efficient NumPy code that can handle larger datasets with less memory.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.